So the next topic that we'll review here continues with the second law of thermodynamics. So it states that entropy of the universe increases for spontaneous processes. So that's the first part here, but the entropy of the universe does not change for reversible processes. And this is defined in these two equations here. So the change of entropy, the change of randomness in the universe, for specifically a reversible process here would be the change of the system plus the change in the surroundings equals zero. So that means that there's net zero change. So there's no change as noted here for a reversible process. And then this second equation for an irreversible process shows that the change in entropy for the system plus the change in that of the surroundings is going to be greater than zero. So there's going to be an increase in entropy or an increase in randomness of the universe. So that's specific again to spontaneous processes. So that's for, as we defined earlier, an irreversible process. So all spontaneous processes, the entropy of the universe increases. So let's look at this a little more in detail here. So there's another scientist, Boltzmann here, and that's actually his headstone, which we can see is inscribed above with his famous equation, where entropy equals the Boltzmann constant times log of W, where W we're going to see is defined as microstates of our system. So he described the concept of entropy on a molecular level. So let's look at something like the expansion of a gas at the molecular level. So that's shown here on this next page. So say we have these two different colored molecules here, red and blue on the left-hand side, and there's a closed stopcock between these two vessels here. And we can open that stopcock, and then there's multiple different arrangements here for specifically that these two molecules could obtain. So these are referred to again as the microstates, or all the possible arrangements of these two molecules. So we could see that the blue is in the left and the red is in the right. The opposite over here, both could be on the left or both could be on the right. So there's four different ways to arrange these molecules. And if we looked at the probability that the blue molecule is on the left, in 2 out of 4 of these scenarios, or half of the time, that's the case. The red is on the left, the same. If they're both on the left, that is only 25% of the time, or both on the right, 25% of the time. So there's different measures of probability. And if we look at the probability of just two molecules, things are pretty simple to define. But say we looked at, the probability of one of these molecules being on the left or right, or rather, say we had a mole of molecules, and we have two different locations, two different sides, but we raised it to how many molecules we have in a mole. We would see that the probability of all of them being on one side or the other would go to zero here. So we're going to look at these different microstates, and they're usually more than two molecules. So we'll try to keep track of as much as we can. So let's define what a microstate here. And again, I've briefly defined it above as the single possible arrangement of all the positions, and also I did not mention all the kinetic energies of gas molecules at a certain time. So we can refer to that as like a snapshot. So these are specific thermodynamic states, again, of both position and kinetic energy. So this is another view that we could take when we refer to state, such as phase. That's controlled a lot by pressure and temperature, and this is generally a macroscopic view. So when we say state or phase, so solid, liquid, gas, Now let's go from the macroscopic view to the micro state. So this will go a little bit deeper, and we'll look at the actual atomic structure or molecular structure. So each thermodynamic state has a specific number of microstates, and that's that W from that equation that we saw above on Boltzmann's headstone. And this equation here is the one that we'll use to reference the entropy of our system. And K here, by definition, is this Boltzmann constant here. So 1.38 times 10 to the negative 23 joule Kelvin. And we won't actually have to do any calculations using the Boltzmann constant, but we should consider this when we think about entropy, when we think about microstates in general. Just note that there are a couple equations here that utilize this relationship, this constant, and we can see the natural log function used as well here. But again, we won't actually need either of these equations on the next exam, but let's look at how or if entropy will increase or decrease with volume, temperature, some of these variables here. But in general, entropy will increase with the increase in number of microstates. So we increase microstates, we're going to increase entropy. So say we increase volume. So there will be more volume, right? So more positions available for those molecules. So in the end, therefore, we can say we know that we would increase entropy as a result. Then we could look at temperature. So if we increase T, we're going to be increasing the kinetic energy of our molecules. And then once again, we would increase entropy. So like so, if we decreased either of these, decrease in volume, we would have less motion available, less microstates because there would be less space. So we would see a decrease in entropy. Same thing with a decrease in temperature, decrease in kinetic energy equals a decrease in entropy. So let's look at some different motions, molecular motions, and energy down here. So if you did not know this before, I'll define temperature as a measure of the average kinetic energy of the molecules in a sample. So that's actually what you're measuring with your thermometer is the kinetic energy of the molecules. And molecules can exhibit several different types of motion. So some of them are listed down here. So there is translational motion. So gases have a lot of this, right? Because they can move. So gases are high in translational motion. This is the movement of a molecule from one place to another. So movement of molecules from one place to another. And next we have what's referred to as vibrational motion. So this is the periodic motion of atoms within the molecule. So there's an image below that I'll show, and then there's also, so this we can say atoms that are bonded. So atoms bonded within a molecule. They're actually bending and stretching and doing other types of vibrational modes. And then we have rotational. So this is when a molecule will rotate upon an axis. So let's take a look. Or we should say an axis or a sigma bond. So a single bond, right? Single bonds. So let's look at some images down here of these types of motions. So vibrational motion, as I mentioned, is atoms that are bonded together. So in this case, we can have like stretching. We can have some other things like wagging or what is this? This is an asymmetric type of stretching. These are all different vibrational modes. And we can utilize those when we do things like IR spectroscopy. We can look at the different vibrational modes of molecules and determine what types of functional groups they have. Then there's also rotational motion here, which I mentioned. Say we have this axis in the middle of the molecule and it's just kind of spinning around. So all of these types of motion lead to the many microstates. And as mentioned previously, as the number of microstates increase, we tend to say entropy will increase as well. So let's look at this in light of some physical states here. So physical states, we can say solid, liquid, and gas. So we have solid water as ice, liquid water, and then water vapor and gas phase here. So depending on the structure, the temperature, we can list some of the properties. So we see rigid crystalline structure in solid ice. Motion will be restricted to just vibrational modes. There's no translational or rotational because they're kind of locked in place here in this crystalline structure. So this would have the smallest number of microstates out of the three phases. So this would be our lowest entropy over here. Somewhere in the middle, we would see liquid water. So there's still some, translation happening here. They're moving maybe slower than gas molecules, but these molecules can move across one another. They are free to vibrate as the crystal, this solid structure was as well. And they're also rotating, maybe on an axis. Like if we drew an axis in the middle of some of these molecules, they could rotate freely. This has a larger number of microstates than our entropy of ice. Then we go on to our highest entropy phase here, the gas phase, or rather the highest S. Molecules are spread out. They are really, separate from one another, independent of one another. They have translational modes, vibrational modes, rotational motion, and therefore this would have the largest number of microstates. So we can say in general that the entropy of a gas would be the highest if we have the same substance that we're comparing, and then its liquid phase is somewhere in the middle, and then lowest entropy would be for the solid phase. So we'll consider this in the next video, and we'll take a look at sample exercise number 3.